Hi everyone, my name is Nikola Rajic. I am bridge designer from Serbia. I am currently employed in DB Engineering company, where I am involved in concrete bridge design. And apart from that, I develop parametric bridge design models and I manage parametric bridge design process. So today's topic that I would like to talk about will be parametric bridge design using MIDAS Civil and particularly using MIDAS Civil NX combined with Python. So today's session will be divided into 3 parts. In the first part, I will give a small introduction into parametric bridge design and what are the advantages of this. In the second part, I will go through a simple parametric bridge model example, and then in the third part, I will scale all this up. I will give example of a full parametric bridge model that can be efficiently used in practice. Okay, so let's continue with the introduction. Bridge design process is usually consisted of 4 main parts or 4 main steps. In the first step, we define our input data. We make our initial assumption of our bridge layout. We may select cross-section type for our main girder, its cross-sectional dimensions. We may select cross-sectional dimensions for our piers, etc. We may have also select whether we have deep or shallow foundation. We have some input data on our loading. And most certainly we have the initial guess for our tendon layout and rebar arrangement for structural members. With input data defined, we continue with the next 2 steps. We perform load analysis and we generate our FE model. During the FE model generation, we need to generate our finite element mesh. We need to apply boundary conditions. Maybe we need to define our construction phasing data, and we need to apply loads that we have previously analyzed. After that, we perform structural analysis. We obtain structural analysis results, which we then use in the 4th and the last step to perform ULS and SLS checks. Those ULS and SLS checks usually do not pass initially for our super and substructure, so we need to revert back to the initial step and to modify our input data. We maybe need to modify our main girder cross-section dimensions or maybe our pier dimensions. Most certainly we will need to modify our tendon layout geometry, and maybe we need to modify our rebar arrangement. After that, we go through steps 2 and 3 once again. We modify our FE model and we perform structural analysis and we go through ULS and SLS checks once again. If they pass now, the bridge design process is completed, and if they do not pass, we need to revert back to the initial step and go through this cycle once again. So what is the idea of parametric bridge design process? The idea is to identify which are the tasks that are being repeated many times during this cycle. These are steps number 2 and number 3. So we generate our parametric bridge design script which automates these tasks. But this script requires the same package of input data as standard bridge design process. But we need to parameterize some of the input data to make it possible for some of those input data to be changed in our parametric bridge design script. Which are those data? This requires some experience. We need to see what will be input data that will most likely be altered during this bridge design process. And then those data will be made possible to change inside our parametric bridge design script. So inside the parametric bridge design process, we are only involved in steps number 1 and number 4. We provide parameters for our script, then our parametric bridge design script performs automatically steps number 2 and number 3 instead of us, and then we are involved in the step number 4 where we check have the ULS and SLS checks passed. If they didn't pass, we revert back to the initial step, we modify input parameters, our bridge design parametric bridge design script performs steps 2 and 3 automatically, and then we only check results in the step number 4. So what are the advantages of this parametric approach to the bridge design? During the manual model creation, engineer goes through the same tasks again and again. These tasks are boring, they require 100% focus, and if engineer's focus is not on maximum level, there is some possibility that errors may occur. And during the automatic model generation, there is zero possibility of these modeling errors to occur. Next advantage of automatic model generation is that it is standardized. Each model is generated the same way. So, for example, structural groups are named the same way. So, if one engineer starts working on a model of a bridge, and then he passes that model to someone else, the other engineer will very easy continue working with that model, because on the same company, everyone is working the same way. Next, maybe the biggest advantage of parametric bridge design approach is that it allows engineers to focus on structural aspects and not on the modeling and using the FE software. Parametric bridge design script does finite element model generation instead of us, so then we do not need to think how to generate FE mesh, how to apply boundary conditions, whether the master node should be the one node or the other node. This is all left to the parametric bridge design script. An engineer only thinks on the engineering structural aspect of bridge design, whether the piles should be extended or not, whether the tendon layout should be changed the one or the other way, etc. And the last and not the least important is that it allows much efficient design. Manual model creation is extremely time-consuming, especially for big structural models. Automatic model generation can generate that same model in very short time frame. And to summarize, the parametric modeling workflow requires the following. First, we need to define our bridge parametric model. For example, we may have a job to design 60 bridges. Then we group those bridges into similar ones. Maybe we define 3 groups of 20 bridges. First group has solid slab main girder cross-section. Second group has double T cross-section. And the third group may have, for example, the box main girder cross-section. Inside each of these groups, we define parametric bridge model. We see inside of these groups of, for example, 20 models, what are those differences between those bridges? Is the difference pile length? Then we choose the pile length to be parameter for our parametric model. Maybe difference is pier height, or maybe the difference is main girder cross-section height. So these are definitions of our parameters for our bridge parametric model. Then this is something like an idea, what we want our parametric bridge script to do for us. Then the next step is to translate this idea into the parametric script, for example, in Python programming language. This task requires basic or intermediate programming knowledge. For extremely general parametric bridge models, this may require advanced programming knowledge. But clustering models and grouping them into several groups and not making one very general model that can cover all possible modifications of the bridge can reduce this problem to the smaller scale, and then programming knowledge that we require is somewhere between basic and intermediate. This parametric script should be done in the way that it is possible for it to communicate with MIDAS Civil or MIDAS Civil NX. This communication is done either directly on the two-way manner. This is usually done using the API, and this is possible in MIDAS Civil NX, or this communication may be only in one way, from script to pass data to MIDAS Civil. This can be done using the MCT command shell, and this is available in both MIDAS Civil and MIDAS Civil NX. So two-way communication is possible in MIDAS Civil NX, and one-way communication is possible in both MIDAS Civil and MIDAS Civil NX using the MCT command shell. Okay, so let's continue with the next section. In the second section, I will go through a simple bridge model and how to generate parametric bridge design script for it. This parametric model has several parameters. For example, it is possible to define number of spans, to define radius of curvature. It is also possible to define main girder cross-section dimensions for this box cross-section type. It is possible to define its material and to define magnitude of superimposed dead loading. This parametric bridge design script will be written in Python programming language, and it will make it possible to communicate with MIDAS Civil NX in two-way direction. It will be possible to send data from parametric bridge design script to MIDAS Civil NX, and then it will also make it possible for parametric bridge design script to read the analysis results from the MIDAS Civil NX. And then we will use those results to make a small-scale parametric analysis for our parametric bridge model. For this example, we will need basic knowledge of MIDAS Civil NX API features. Let's start with the most basic command on how to generate new project. MIDAS API manual has detailed documentation on each of these commands. For example, how do we use this command? We will use it via calling this MIDAS API function. It requires 3 arguments. First argument is type of the method. Here it says that type of the method is post, so we type post as the first argument. Second argument, it requires from us to define which command it is. Here it says doc/new, so we type that as the second argument. And the third argument is the body of the command. So for this new project command, there is no body, so the body is just open and closed curly brackets. So let's see how to implement this in MIDAS Civil NX and Python. I'm using Spider as the IDE for Python. First, we import requests. Next, we define function for MIDAS OpenAPI. Here inside this function, we define base URL and MAPI key from the corresponding values here in MIDAS Civil NX. First, in the apps, we connect our API, and then we go to the API settings and copy the base URL and the MAPI key right here in this MIDAS API command. Next, as you saw earlier, we need to define body of this command. In a separate variable, we define body for this new project command, and it is just open and close curly brackets. Next, in a new variable, we call our MIDAS API function. As the first argument, we type the method type, it is post. In the next, we define command. The command is /doc/new, and the third argument is body. We already have it in a separate variable that is called new file_JSON, and we call it as a third argument. Now we can run this script. We just click here, or we click F5 and we run this command. And as you can see here in the MIDAS Civil NX screen, it is just creating a new project. Okay, let's check out now another command. Let's see how to define units with MIDAS Civil NX API. Pattern is the same. We already saw how to use MIDAS API function, so we use it again. First, we define method. Method is now get or put. Get method will take information which units are already defined, and put method will define new unit system. So we will use put method here. command is /tb/unit. And what is the body? Let's check out the MIDAS Civil NX API manual. It says this. We need to define several things. This is the pattern for unit body. First, we define which is unit for force system, and you see here in a further explanation that it has several possibilities. We will use kilonewtons. So first, unit for force is kN, and unit for distance we will use meters. So unit underscore dist will be capital M. So we define our unit underscore JSON that we will use as the body in our MIDAS API command. Unit JSON, we use this same pattern, and here under dist we call our defined variable unit underscore dist, and here for force we use our already defined variable unit underscore force. Okay, let's check this out now in MIDAS Civil NX. Here we will define unit dist and unit force variables. Here we generate the unit underscore JSON variable for the body of the MIDAS API command, and under the unit underscore res we call MIDAS API function. First we put in the method as put, next we type in the command, and third we call this unit underscore JSON as the body for this MIDAS API command. Let's check this out now. Let's run this script. It will first open a new project, and then for this new project it will assign new unit system. It will assign for the distance units meters, and for force units kilonewtons. Let's check inside MIDAS Civil NX which unit system is defined. As you can see here in the bottom of the screen, kilonewtons and meters are set as units for our new project. Let's continue now with our parametric script development. As you can see here in the top of the script, apart from request library, we have also imported the math library, which we will use later inside our script. As you saw earlier, we have prepared two parameters for distance units and for force units. In this part of code we have defined parameters of our parametric bridge design model. Length parameter is actually the span length in meters. We have parameter for number of spans, we have parameter for alignment radius, and we have also parameter for superimposed dead load magnitude, which is -30 kilonewtons per meter. We have two parameters for material data definitions. We have material standard and material grade. Here we have prepared ID parameters. We have material and section IDs, and also we have two important IDs for start node and for start element. From these two we will increment later inside our script. As you saw earlier as well, we have prepared body for the new file command, which is open and close curly brackets. We have prepared also earlier the body for the unit definition command. We call here earlier defined variables for distance and force units. Here we define body for our material definition commands. Here we call material grade and material standard. In the following block of code, we define body for the section definition command. Here we have hard-coded dimensions for our box type cross-section. We can also parameterize each of these dimensions. We just need to define a variable here and to put it inside this block of code as a parameter. In the following block of code, we have defined the model geometry. We start by definition of nodal geometry data. We calculate nodal coordinates. Since the main girder is following arc geometry, we have used the math library to calculate its nodal coordinates. In the next block of code, we define nodal local axis. Since the bridge geometry is curved, we have defined nodal local axis such that the nodal local x-axis follows tangent on the main girder and local y-axis follows the perpendicular direction, the radial direction on the main girder alignment. In the next block of code, we define body for the element creation command. We go through the for loop for the range of number of divisions, where the number of divisions is total number of elements for our main girder. Inside this variable, we define body for the element definition command. We call the material ID, section ID, and for the node parameter, we type start node ID and end node ID. As you can see here, we call this variable start node ID defined earlier, and we add I to it, where I is in range of number of divisions. For the end node, we start also with start ID, we add I, and we also add another one to this number. In the next block of code, we define boundary conditions. As you can see, for the first supporting node, we constrain the following degrees of freedom. We constrain all three translations, but as well, we constrain also rotation about nodal local x-axis, that is actually the torsion in the supporting node. For the all following supporting nodes, we run through with this for loop and we define similar boundary conditions, except for the first degree of freedom, translation in x-axis, which is free for the remaining nodal supports. In the next block of code, we deal with loading. We define two variables. Inside these variables, load case name, we define a list with load case names. First is DL and the second is SIDL. In the next variable, inside this list, we define descriptions for these load cases. The first one is dead load and the second one is superimposed dead load. In the next block of code, we run through a for loop with a range, with a length of this list with load case names, and we define body for the command to define static load cases. Here we type the name for the static load case. We take the ith element from this list. Since it runs through these both values, in the first run it will take DL, and for the description it will take dead load, and in the next run inside this for loop, for the next, it will take the name SIDL and the description superimposed dead load. Inside this block of code, we prepare body for the command to define self-weight. As you can see here, the -1 is typed for the global Z direction for the load case with the index 0, and that is actually the dead load. In the next block of code, we create body for the superimposed dead loading, that is actually the element loading. As you can see here, it is applied on beams as uniform dead load in the global Z direction, and the magnitude is called here, it calls the parameter defined as -30 kilonewtons per meter. In the next block of code, we create data regarding load combinations. We prepare body for the command to create load combinations. As you can see here, we define first one variable as a list with two items, both equal to 1.35, and inside this block of code we define body for this load combination generation command. As you can see here, it is one combination, it is called comb1. It contains two load cases. First load case is load case name on the index 0, that is dead load, and second one is load case name with index 1, that is superimposed dead load. Factor for dead load is taken from this list from position 0, and for superimposed dead load is also taken from this list, but from position number 1. After that, we save our model, we prepare body for command save as, and here for the argument we type destination of this file and its file name. Next we perform the analysis, we prepare body, which is open and closed curly brackets, and here we prepare body to check some of the results. I have chosen to display reaction forces. Here we define that it should be displayed for the DL load case, that is actually the dead load case, and the component to display is MX, that is actually, since it follows the nodal local axis, it is torsional moment on the supporting node. And in the last part of this code, we actually call all of these commands. As you can see here, first inside this variable we call this function MIDAS API, and we use the body for the new file, and for all the following commands we define units, we create materials, we create sections, we define nodes, elements, boundary conditions, nodal local axis, we create load cases, we define self-weight load case for the dead load, we define beam loading for the superimposed dead loads, and then we generate one load combination, save the model, perform the analysis, and display results. As you can see how this script is organized, it's actually organized that until this line of code, we just prepare a body for those commands. And after this line, we just call these commands one by one. As you can see, they are arranged, but they are arranged almost in the same way as it will be done if we created this model manually. We will first create manually units, then materials, etc. And now this parametric script does all of that instead of us. So the model generation is automated based on some parameters that are set here, and also based on the other required input data that is hard-coded. So this parametric script can be made more complex if less parameters are hard-coded and more parameters are made possible here to enter. This script is now ready to be executed. So I will execute this script by pressing F5. The analysis has been successfully completed, and as you can see, the requested results are displayed right here. The torsional moment reactions at each supporting node are displayed. And just to mention that these are torsional reactions from dead load, which is a vertical, uniformly distributed load. And if this bridge was straight, these moment reactions will be 0, but since this bridge is curved, it follows an arc alignment, these reactions are non-zero. And the smaller the radius, these torsional reactions will be greater. And it might be interesting to see how are they correlated with radius of curvature. we can set few values for radius of curvature and run this analysis and store the values of this torsional reaction and then plot them against the alignment radius. We can do this very simply using this parametric script. Just put all of this code inside one for loop and run this for loop through the radius range. I have created here one variable which contains radius values ranging from 100 to 3000. And we just go through this list, and for each run we change the value of the radius. You see it here. The radius, alignment radius value, takes value that is on index radi position, and index radi is looping through the range of length of this list. So for the first run the radi will be 100, for the next run radi will be 150, and so on until the last value where the radius will be 3000. RF val is right now an empty list, and we have created new body for new command that will take the results from MIDAS Civil NX and store this moment reaction for each radius value inside this list. So the first value stored here will correspond to the radius of 100 meters. The next value stored here will be moment reaction for the bridge with radius 150. Just to check this out, let's see this new body for this new command. Okay, this rf_table out is body for the command to export table results, and in this block of code we read this output data. And here we have added the block of code to plot the mx reaction against the radius of curvature. To plot all of this, we needed new libraries, so we have imported the matplotlib, numpy and cpy libraries. So let's execute this script now and let it loop through this radius range. Okay, so parametric analysis are finished, and let's check the plot that is generated. Okay, so on this plot you have data points represented by squares. Each of these data points represent results of each parametric analysis performed in the MIDAS Civil NX, and this spline curve is interpolated between these data points using the library cpy in Spider IDE. And below this you can see first derivative of this spline curve. It is generated in order to see where this spline curve representing torsional moment reaction versus curve radius is starting to bend. In other words, we want to know in which range of radius torsional moment reaction starts rising significantly. This is important for us to know at which radius it is important to model bridges as curved. We all know that for bridges that have large radius, we can model them as straight. we can ignore this radius. But if you see the first derivative, you can see that it starts rising somewhere between 1000 and 1500 curve radius. So this spline curve starts bending somewhere around here. So it may suggest that bridges that have curve radius in this range and smaller need to be modeled as curved, because they start generating larger torsional moment reaction only from vertical loads. There is also one more analogy. If we compare Eurocode, which says that for bridges with this curve radius, somewhere between 1000 and 1500, you need to start applying centrifugal forces as well. So this can be one analogy between this analysis, modeling of these bridges, and Eurocode on centrifugal forces. With this analysis, we conclude our second part of presentation with live example of a simple bridge parametric model. We continue with our third part, where we demonstrate full parametric bridge model in action that can be fully utilized in engineering practice. In the next sketch, you can see what are the features of this full parametric bridge model. It is developed in order to be as general as possible and to cover the vast majority of bridges with two main girder cross-section types. The first main girder cross-section type that is available is the T-section main girder with multiple ribs, and the second main girder cross-section type is composite I-section. It consists of prefabricated I-girders and a cast in situ slab. Also, for this parametric model, all of the alignment geometry is fully parameterized, so user can enter spans, number of spans, and span lengths are fully parameterized. All of the parameters for this bridge model are taken out from the script, and they can be entered separately in a spreadsheet that looks something like this. It is divided into separate tabs. For example, for this mg_geom tab, user can define span data. Row by row, user defines span length for each span. And here, for the variable mg cross-section key, user just needs to select from the drop-down menu one of these two values. One value is 0 and the other value is 1. And what those two numbers mean: for each tab there is also an input guideline, and in this input guideline each of the variable is explained and some guidelines are given for the data input. For example, for this mg cross-section key data, here you can see that user needs to enter section key for main girder, and that 0 means that the main girder cross-section type will be T-section. It is cast in situ, and the number 1 will be the I-section type, that is main girder type with prefabricated I-sections and the cast in situ slab. And if we now start modifying the spans data, if we, for example, delete the last two spans, you can see that here on this sketch, the plan view of the main girder geometry is adjusted. If we now go back and add one more span, one span is added here as well, so the user can preview his main girder geometry. There is also possibility to define web haunches. It is possible to define separate haunch at the outside and on the inside of the web. Also, web haunch length and widened length is also parameterized. There is possibility to define global skew angle for the bridge, as shown in this sketch. If user decides to define a global skew angle, then each supporting axis will be rotated by that same angle, but there is also possibility to alter the support axis rotation for individual piers by this additional pier rotation angle. There are two types of bridge piers available. The first type is the so-called bearing pier, where the main girder is supported via bearings. The number of bearings and spacing between bearings is fully parameterized. The second type of bridge pier is the so-called rigid pier, where the connection between the main girder and the pier is rigid. Number of piers as well as spacing between piers is also fully parameterized. There are three cross-section types available for the pier columns. There is rectangular, box and circular cross-section, with its dimensions also fully parameterized. All of this data regarding the bridge piers is also taken out to the spreadsheet, and it can be entered there, and then it is imported inside the parametric script. In the sup_data tab, users can define bridge pier data. Inside this block of input data, user is required to enter data for piers that provide rigid connection to the main girder, and inside this block of input data, user is required to input data for piers providing support to the main girder via bearings. Underneath this, you can find the input guidelines that provide detailed guides for each of the input variable. Under the guidelines, there is also a sketch for the so-called pier rigid and for the so-called pier bearing. And on the right, you can see the sketch that provides further explanation and clarification on each of these variables graphically. Regarding the abutment geometry, there are two main possibilities. The first possibility is to define an integral abutment. An integral abutment will provide a rigid connection with the main girder, and the second possibility is a semi-integral abutment, which provides support to the main girder via bearings. Also, the geometry of the abutment is fully parameterized, both for the wing walls, for the front wall, for the parapet, and for the pile cap as well. And also, for the semi-integral abutment, number of bearings and spacing between bearings is also fully parameterized. All of this data is available for input inside the same spreadsheet. In an input Excel spreadsheet, under the tab abut_data, there is possibility for the user to enter all the required input parameters for abutment geometry generation. On these three sketches, there are further graphical clarifications for each of these variables for the semi-integral abutment. As you can see on these first two sketches, there is possibility to define two types of wing walls as well. And on the third sketch, you can see further clarification for the front wall geometry parameters. This is followed by input guidelines as well. Under the next tab, integral_data, there is possibility to define whether the connection between the main girder and the abutment is integral or semi-integral. This drop-down menu gives us two possibilities, 0 and 1, and the input guideline clarifies this further. So option 0 means that the connection is semi-integral, and the option 1 means that connection is integral. Under this guideline, there are two sketches that further clarify geometry parameters for an integral connection. And as you can see on these two sketches, there is also possibility to have a pile cap defined or to not have this pile cap in an integral abutment. There is also possibility to define an expansion joint pier on left, right, or on both sides. As you can see on this sketch, here it is defined on the right side, so the abutment geometry on the right side is omitted, and the remaining non-modeled part of the bridge is substituted with corresponding springs that user is required to define. Next important feature of this parametric bridge model is that it automatically performs load analysis and generates all of the load data and information regarding bridge design. For example, it generates automatically dead load, superimposed dead load, temperature load cases, wind loading, as well as it performs a detailed traffic load analysis, and it automatically generates all of the moving load cases. Also, it automatically generates all of the seismic load cases, and it automatically combines all of these loads and generates load combinations required for design according to Eurocode. User has also possibility to define data for pre-stressed concrete and reinforced concrete members design. User enters longitudinal reinforcement data and shear reinforcement data, and parametric script automatically generates input required for MIDAS Civil and MIDAS Civil NX to design these members. Apart from that, there is also possibility for automatic tendon data generation, in which user inputs the basic data that is required, for example, eccentricities in span and at piers, and this bridge parametric script automatically enters nodal coordinates for those tendons and prepares input data for MIDAS Civil and MIDAS Civil NX. Inside the Excel input spreadsheet, for the next few tabs, user is required to enter the shear reinforcement data for span cross-sections and for the pier cross-sections, and also user is required to enter longitudinal reinforcement for both span and pier cross-section. For example, inside this tab, user is required to enter the tendon geometry data, and for this tab, user is also required to enter strands data for prefabricated I or 3 girder cross-sections. So with this, we wrap up an overview of this full parametric bridge model and its features, and in the next presentation we will go through a sneak peek of implementation of this parametric script in practice. So using Parametric Bridge Design Toolbox with MIDAS Civil requires, in the first step, to input parameters in an input Excel spreadsheet. We define bridge geometry, soil conditions, construction phases, rebar, tendon data and loading. After that, we publish data for model generation. After the model generation is finished, we import data in MIDAS Civil and we run analysis. After the analysis is done, we check the results. If we are satisfied, bridge design process is finished, but if we are not satisfied, we revert back to the input stage and modify parameters and go through this cycle once again. As you can see, after the model generation, zero manual work is required. All of the data, for example, for superimposed dead load, for temperature rise, and for braking loads, etc., is automatically generated. Also, data required for tendon generation is automatically generated, and it follows possibly the construction stage data that we may have defined. All that is needed after this is to perform analysis and check results. With this demonstration finished, we come to conclusion. We can say that MIDAS Civil and MIDAS Civil NX, with the introduction of the API functionality, brings more possibilities for bridge design. Most importantly, it opens gate for parametric bridge design process, which then introduces its own advantages into the bridge design. For example, it significantly reduces margin of error, it standardizes bridge design process, and it allows an engineer to focus on engineering and structural aspects of the design, and it provides more time-efficient solutions for bridge design. Thank you for your attention.